All right, so now in this video, I'm going to show you I'm going to show you the Bellman-Ford algorithm. And this is our graph. I just draw it like this. And so it's pretty similar to BFS, but it has some difference. And so BFS, as you know, works only with the graph which is unweighted, and Q-based Bellman-Ford can work with a graph with weights and also with negative weights. So, for example, Dijkstra cannot work with graphs that has negative weight in, but in case of Q-based Bellman-Ford, it is not a problem. Okay, so this is our table. So our table will have one more additional column, which will be called Q. And here we will put our vertices. So that's why basically the algorithm is called Q-based. As the starting points are the same as in the previous algorithms. The only difference is that in this algo, we also have this E value, which is just a counter for the edges. And yeah, let me just go through this. So as you know, in the task description, the vertex Z was the source. So we will just start from it. And inside the Q, we will have Z inside. And the initial value of Z is going to be 0 for D and 0 for E. And it's all the parents of all the nodes are null, as usual. And then we look at this node, and we see that it has outgoing H2 X and S, and we put them into the queue following the alphabetical convention. So we put first X and then S. So in the start of the queue, we will remove S. And then we see that from C to S, we can get in cost 2. So we write 2, and after the comma, we write the number of edges. So it's like 1, so we just write 1. And we do the same for X. So it's going to be 7 and 1. And when we take Z from the queue, we have to put its children into the queue if they have shorter paths. So for example, 2 is smaller than infinity, 7 is smaller than infinity. That's why we will put them into this queue. And in the next iteration, we're going to take out S, and S, D, and E values 2 and 1, as in here. And we basically do the same thing. We look at S, we have an H2 T and Y. So 2 plus 6 is going to be 8. And as you can see, we have one edge here, second edge here. So that's why it's going to be 2. For Y, it's the same. So 2 plus 7 is 9, and the number of edges is 2. So we update them here, here, and of course, we need to put this T and Y into the queue because we have found something smaller than infinity because their previous D and E values were infinity. So we put them in the alphabetical order. So first T and U, Y. We take out X from here. And X values are 7 and 1. And then we look at x, it has an edge to t only, and so it has a cost 7, and if we plus minus 2 to 7, it's going to be 5, and the old cost of t is 8 and 5 is smaller, so we write 5 instead of 8, and but the e value is going to be 2. Why? Because we go here 1, and from x to t, it's going to be the second edge. That's why it's 2. And we update the parent of t to x. We don't add t again because we already have it in the queue. So if you look at the algorithm, it says if not in queue, then add. If it's already in the queue, then just skip it. So that's why we're here. We need to skip it. And we take out from queue t, and t's values are 5 and 2. And we look at t, it has an edge to x, y, and z. And let's count. So 5 plus 5 is 10, but our x has cost 7. So 7 is smaller than 10, then therefore we do not change it. And then 5 plus 8 is 13, and y has cost 9, so also no need to change it. And as for z, it's going to be 5 minus 4, but we have 0 and 0, so it's not a better option. So we don't do anything in this iteration. And then we take out the y, because in Q we still have y. So we take out y, and its values are 9 and 1. And we look at 9, it has one outgoing edge to C. C and 1 to X. And so what we do is we add this value, so 9. Wait a second. So it has 9 plus 3. Okay, yeah. So this was the y's path. 9 plus 3 is going to be 6. And as you can see, this is 1, 2, 3. So 3 edges, 6 and 3. So we update it here and we change its value. And as for z, it's going to be 9 plus 9. And this is not smaller than 0 and 0. So we do not change it. And we put into the queue x, because this was its new cost is smaller than this one. That's why we add it to the queue, but we don't add c because it didn't really have smaller cost. So in the queue we have x now, and we take it out. We look at x, and it has only this outgoing edge. And what we're going to do is we have this cost 6, we add minus 2 to it, and we get 4. And it's the number of edges going to be 4, because if you look at x, we know that its parent is y. So this is one edge, and y's parent is s. second edge, and S parent is Z, third edge, and this is the fourth, so it's going to be 4. Okay, so and we add this T to the Q, and then we take out from the Q with its value 4 and 4, and we go to T, and we have this 3 edges, and 4 plus 8 is 12, and 12 is not smaller than 9. 4 plus 5 is 9, but we have 6, so also we do not do anything. And 4 plus minus 4 is 0, but it's already 0, so no change here. And we do not put anything into the Q, and Q becomes empty, and this will terminate the algorithm, and these are going to be our final results. And these are the parent corresponding parent values. Yes, and I will also double check this solution with professor, and that's it.